The supersymmetry, briefly the Susy, is extended symmetry, including the transformations between the fermion particle and the boson particle. And typically the simple supersymmetry is n equal 1 supersymmetry, where n represents the number of the supercharges Q. So if the Q acts on the fermion state, it becomes a boson, and vice versa. Fermion carries the spin 1/2 particle spin into the half into the spin, and the boson particle carries into the spin. And we can extend this, that is n equal 1 supersymmetry, to the n is larger than the 1. This means that the number of the supercharges is the now the larger than the 1. So there are multiple supercharges with the index capital I equal to the 1 to the massical n. So now there are multiple supercharges Q and the Q bar with the I index. So add this to the Poincare generators for the space-time symmetry. P corresponds to the momentum, and M meaning correspond to the spin and the boost. So we can extend this to the N is rather than the supersymmetry algebra. So the first three lines that correspond to the Poincare algebras of the special relativity theory. The commutators of the momentum P and the spin operator. And the second block, second three lines includes the commutator relations between the PM and the supercharges. And the binary blocks includes the anti-commutator relations between the supercharges. So this unequal greater than 1 supersymmetry algebra also tested by the Z2 graded real algebra structures. We can assign the even numbers for the momentum and the spin operators, and the odd number for the supercharges. Then for the even and the even generators, the commutator relations are given, and also the even and odd operators, the commutator relations applied, but for the odd and the odd operators, the anti-commutators relations are inserted. And especially for the different supercharge index I and J, we can assign some antisymmetric complex matrix Z. This is called the central charge. The central charges are commutated with all the generator. And we'll talk about what is the laws of this central charges Z. But before going to the these topics, let's talk about the unequal 1 supermultiply. How the eigenstates turns out in the simple unequal 1 supersymmetry algebra. One can take the Clifford vacuums, capital omegas, with the spin state J and M, and also can impose the such a Clifford vacuums becomes analyzed if the Q eigenstates are on this state. Then if we use the commutator relations between the spin operators and the supercharges, then the spin can be lead off from the generators M. So from the commutator relations, if the supercharges are acted on the site, then this changes the spin with the plus 1/2 or minus 1/2. So this makes the if the supercharges are acted on the the states, then the spins states that changes by the plus minus 1/2. So this makes the supermultiplot with the carry the same numbers of the Casimir's invariant quantity, but this multiplus includes the different state with the spin plus minus 1/2 changes. We can assign the j equal to the juice as a simple example. Then the Clifford's vacuums, original ones, carry the j equal zero spin state, and azimuthal spins numbers m is automatically zero. But if we ask the q1 and the q2, now the spin state becomes plus minus 1/2. This means that now the j becomes 1/2. So these supercharges eventually change the boson and the fermion niches. Originally, the state was a boson, but now, after acting on the supercharges, this becomes a fermion. And if we ask the supercharge 1 more times, then it becomes a boson. And due to the Grossman numbers identity, the squares of the Grossman number set is equal to the 0, so the same Q1s acts on the Clifford's state automatically 0. And also we know that the anti-commutative relation between the Q1 and the Q2, so the acting on the Q2 and Q1 yield the same state. So the only possible states is this both state. So for the j equal 0 supermultiplot, this corresponds to the 2 bar spinner and 2 complex the 2 scalars component, but the binary scalar components correspond to the pseudo scalar. So if we combine these scalar components, we can construct the complex scalar. So this j equals 0 supermultiplot, there's a one complex scalar and a bar fermion. This is called the Cala supermultiplot. If we consider the j equal 1/2, then the original ones carry the spin 1/2. But if we act the q, then the one goes to the spin 1 and the other ones go to spin 0. And if we act the supercharge 1 more times, then the spins return to the 1/2. Now there are also the 2 bar fermions component and the spin 1 and the 0. So that this multiplus contains the vectors and the 2 bar fermions and the little scalar. This is correspond to the vector supermultiplot. So by using these 2 supermultiplot, one is the chiral supermultiplot and the other one is vector supermultiplot, we can construct the unequal ladder and the 1 supermultiplot. The next simple example is unequal 2. Now there are the 2 supercharges. Capital I is equal to the 1 and 2. And for simplicity, we'll assume that the central charge is 0. So here, the right hand side is 0. Similarly, both the 2 supercharges that change the spin shifted by the plus minus 1/2, but azimuthal angular momentum's numbers And now there are several choices to ask the supercharges. For example, for the first level acting on just the 1 supercharges, there are 4 possibilities because there are Q1, Q2, and there are index I. Capital I contains the 1 and 2, so there are 4 states. And if we ask the 2 supercharges, there are 4 types of the supercharges here. So there are 4 C2, so there are 6 states, 6 possibilities in here, 6 cases. And also for if we ask the 3-1, and if we ask the 3 supercharges, then there are 4 cases. and there are only one possibility to ask the Bohr supercharges. So we have now the 16 um, states in the one supermultiplier. If we consider unequal to Bach-the supermultiplier starting with the J and M is equal to the 0 and the 0. And in the level 1, there will be the spin 1/2 particle, and in the level 2, there will be the some spin 1 components and some scalar component. And now the level 3 spin 1/2 weakens, and the final level 4 the scalar particle with the spin 0 weakens. So there are various components here, so step by step. In the level 2, there are spin 1 state, the gauge boson, and the additional scalars here. So this makes the gauge boson, and the remaining one is scalar. And the level 0 and 4 gives the remaining scalar state, and the level 1 and 3 gives the 2 bar fermion. So in the unequal 2 Bach-the supermultiplier, there are 1 unequal 1 Bach-the supermultiplier and 1 unequal 1 color supermultiplier. So here's and here's. We can decompose like that. So there are 1 gauge boson and the 2 bar fermion because R is 1 equal 2 and the 1 scalar component. And also we can consider the hypermultipliers in the unequal 2. We can impose the BPS conditions. So only the 1/2 of the supercharges that accelerate non-trivially. For example, we can make the Clifford states balances when the Qi daggers was I equal to the 1, 2. But if the QR pass to the 2 section on the Clifford's vacuum size, then this unlighted, but not for the QR pass 1. Then this makes the level 3 and the level 4, there should be the automatically Q2R pass included in here, so that above the level 3, the state becomes 0. So there are only the 2 complex colors and the 2 bar fermions in this state. There are no spin 1 particle in here. So in the unequal 2 hypermultiplier, there are only the unequal 1 color supermultipliers in the decomposition. In generally, now we will go to the unequal 3 and the unequal 4 supermultiplier. If we consider the massless supermultiplier and each the supercharges, so-called fermions, including operators, change the spin or helicity, because now we will consider the massless state. We will say the helicity rather than the spin, and the helicity is decreased as 1/2 from the highest helicity lambda max. So the multipliers now includes the helicity from the lambda max to the lambda max minus n equal n over the 2. And we'll record the CPT invariance so that there should be the opposite helicity. So the minimum of the lowest helicity should correspond to this lambda max minus n equals over the 2. And for simplicity in this test, we will not include the gravity. So the highest spin is at most 1 because spin 3 over 2 and the spin 2 requires the gravitons or gravity now. So by imposing these conditions, there are no gravity, then the lambda max are equal to the 1, and also lambda minimums is greater than minus 1. So the 1 minus n over the 2 is greater or equal to the minus 1. This gives the results of the number of the supercharges. The current n's is the smallest or equal than the 4. So we will consider n equals 3 and the n equals 3 and n equals 4 supersymmetry algebra. For the n equal n is rather than the 4, this requires that the the magnitude of the Hamilton lambda is rather than the 1, recall that the mass loss gravitinos or the graviton. So the largest spot charges such algebra recall that the gravity is there automatically. If we one can allows the graviton, then the lambda max now becomes the 2. The graviton carries the spin 2. So the now the inequalities changes to the following form. There are 2 in the lambda max and the minus for the lambda minimum, and the number also of the supercharges that are constrained by the last order equal to the 8. So the maximal numbers of the n is 8 in the including the gravity, but this is only the case of the Bohr dimensions. So for example, if we consider the Bohr dimensions n equals 3 mass loss factors per multiplied, then it starts with the 1 spin 1 becomes a spin 1 half, zeros minus 1 half. Under the multiplicity, the case is just a 1 3 3 1. And also there are speed conjugate for the this helicity state. So the by the component build notations, there are spin 1 particle parameters with the index I equal to the 1 and 2 and 3, and the scalar particle also the bar index ij is 0 1 2 3. And because the for the scalar index ij is antisymmetric by the exchanges, so there are only the 3 degrees of freedoms in here. So the n equals 3 vector multiplied can decompose it into the n equal 2, like the n equal 2 vectors per multiplied and n equal 2 hypers per multiplied, because there are 1 gauge bottom fields and the 2 bar fermions and the 1 real scalar fields in this state, and n equal 2 hypers multiplied. There are other parameters here like that. And yeah, why there are 3 multiplicity here? So yeah, because of ionic consider n equals 3 supercharges in the mass loss case. And also we can realize that the decompositions in the n equal 1 language, because n equal 2 vectors supercharges that decompose it to the n equal 1 vectors and n equal 1 color, and this decomposes n equal 1 color, n equal 1 color. So there are n equal 1 vectors and 3 n equal 1 colors per multiplied in the n equal 3 vectors per multiplied. For the n equal 4 vectors per multiplied, now the multiplicities changes. The case is given by the 1, 4, 6, 4, and 1. And now the component builds for the spinor field. There are 4 multiplicities here, and for the scalar one, there are 6 multiplicities in here. Also the antisymmetrics for the changes of the index, so only the 6 degrees of freedom. And the n equal 4 vector multipliers that decompose in the 2 n equal 1 n equal 2 vector super multiplier and the n equal 2 hyper super multiplier. So this is automatically same with n equal 3. Because n equal 3, there are CPT invariant. To satisfy the CPT imbalance, there should be the CPT conjugate state. But in the automatically n equal 4, this includes the CPT self-CPT conjugates. So the n equals 3 back super multipliers and n equal 4 back super multipliers the equivalent. Such a multiplicity can be obtained by the C case here. And in the final part, now we'll talk about the additional extensions by including the central charges, non-zeros right-hand side for the anti-commutative relation between the different supercharges index of the I and the J. Central charges are written by the jet, with index of the capital I and the J, and they satisfy the anti-commutativities by exchanges of the index. And the central charges that commutes with all the Poincare generators P mu and mu nu, because this is the center of this group. In the presence of the central charges at ij, there should be the positives constraint. The other words, in the unitarity. For the any given complex phenocide, they should satisfy the positives bound. This gives the bounds to the mass m and its central charge z. So we can write some state psi, and the complex numbers and the supercharges can assign to the us the same quantity. Then the dispositive, the unitarity conditions can be written like this form, and the same to this anti-commutative relation. And if we consider the last sublime, then the anti-commutative relation between the Q supercharges and the Q daggers becomes just given by the last mass m. Originally there is a p missing here, and still the anti-commutative relation between the supercharges qi and the qj's have the z. For example, if we consider n equal 2, and by considering the because that ij is complex, we can write that as a polar coordinate notations, and one can define the combinations of the q1 and the q2 as the a and the b, including the pace of the central charge z. And one can compute the anti-commutative relation between the new operators a and the b. So here is the original one, and by defining the a and the b, now the new commutative relations given like that. Because this is just a linear combination, so also the right hand side becomes a linear combinations, and some pace terms opposite each other, and only the radial paths remain. So now the anti-commutative relations between the new operators includes the m and the z. And if we ask the b for this positive constraint, then automatically the positives constraints gives the following inequality: m minus the magnitude, the radial parts of the central charge z should be the larger than the 0 or equal. So the m is larger or equal to the size of the z. When the equalities hold, then this automatically the commutative relation between the b and the b daggers becomes 0. And that this can give some constraints if you consider some BPS state. So today we talk about the extended supersymmetry by adding the additional supercharges for the unequal 1 supersymmetry algebra. In the fourth dimensional, the most popular one is unequal 2 and unequal 4, or that is an unequal 3 is equivalent to the unequal 4. And if we include the gravity, like the local supersymmetry, then we can maximize to the number of the supercharges to the unequal 8. And also the additional possibilities is central charges or the anti-commutative relations between different supercharges. And this gives the some inequalities between the particle mass and the central charges from the unitarity bound, and this can provide and constrains some specific BPS states of the supersymmetry algebra. So today we talk about the n equals rather than the 1 supersymmetry algebra, and this is the first gate to go to some extended supersymmetries and the gauge theory.